Hello everyone, I'm MD Farhad Reza. I'm an associate professor of computer science in Eastern Illinois University. My undergraduate student Ali Kelly worked with me in this paper on dementia prediction using the convolutional neural networks. We know that dementia is affecting so many people worldwide. Early detection is important for slowing the progression, improve the quality of life, and existing model face challenges with imbalanced and heterogeneous MRI data. In this work, it targets three biomarkers: atrophied hippocampus, white matter yeah, hyperintensity, and large ventricles for dementia prediction using the convolutional neural networks. And so in our framework, we collect the data from the Mayo Clinic MRI data sets, and we apply some resizing and technique, and also normalize the data to improve the learning stability during training. We also apply data augmentation to reduce or to address the MRI variations, and our CNN models are here used for classification. We train them and also test them and find out which one is performing better. So in our solution, major thing is that uh, we are stacking many slices together, 38 MRI slices to capture the 3D brain changes that single slice may not capture that. And every image is 256 by 256 pixels. And we, as we use the CNN networks, we know that CNN can learn the hierarchical features starting from the initial layers, capture the local features, and then in the future later layers capture the global features of the biomarkers for dementia prediction. And you also apply on-the-fly augmentation and weighted random sampling that we use for class imbalances that we have in our data set. And we also use the MSc loss function. Uh, so, uh, so use the for we have in our data set we have a huge class imbalance, 87% healthy, 12% mild cognitive impairment, and 1.5% only dementia. So we use the stratified sampling so that in our training set and testing set we'll have the same proportion. And we use the, as you mentioned, weighted random sampler that we're using to increase the selection of the or probability of selecting minority classes when you train our CNN. Right. So, for example, in this case, we use, I think, 33% probability for selecting so that we can sample our different classes equally to improve their prediction. And on-the-fly augmentation that you have mentioned, that we use the random rotation, horizontal and vertical flipping, so that even though there are some variations in the MRI slices, we can address that here. Now, one important thing is that we use the MSc loss function because we also use the cross entropy, but MSc performs better. It's it seems to be because of the severe class imbalance that we have. And we use the four CNN variants that you mentioned before, and everyone has different kernel sizes, different number of channels, different number of convolution layers, and CNN1 you can think about as a baseline. It has the lowest number of parameters, but CNN4 has the highest number of parameters. One important thing to mention here is that normally in the convolution layers, we use convolution neural networks. We use the last layer as the fully connected layers, But in this work, we use the global collapse convolution layer at the last layer. And here, this actually helps to reduce the number of parameters, 11% less than the FC layer that doesn't have any other hidden layer. But if we introduce another hidden layer in our FC layer, then it can significantly increase our number of parameters and put pressure on our memory storage. So layer-wise transformation, we have we showed here 7 layers, 7 operations. First one is the input, and and last layer we using the 26 by 26 kernel for and finally we're going to have a single scalar value. And and most important thing is that to show that our receptive field growth, how the it can CNN can see the initially local features, and then with the increase in the sizes in the layers, it can see the bigger pictures, whole brain images. It can see with the 262 pixels. This mirrors the visual cortex hierarchy, and as you mentioned, the data set already, and in Mayo Clinic data set we are using, and the data we are getting from there is the digital imaging communication medicine format, and we converting to the PNG. And I already mentioned that we are using the normalization, geometric augmentation, stacking slices, and also stratified sampling that we are using. So you're using the in the PyTorch simulation implementation, and we are using batch size 3 because of the because if we increase the batch size from 3 to more, it will put pressure on the GPU, and because of the limitation, we use only 3 images. Then we know that every image is 256 by 256 pixel, and we have a 38 channels. So you're using 3 images per iteration. And you're using training loss, accuracy, precision, and recall power classes for our evaluation. And we use the 20 epochs for training and testing. Every time we do the training in every epoch, we also get our test performance we calculated. And we found out the CNN4 achieved the best performance, 77.4%, and others has better performance as some maybe in the earlier epochs, like a CNN1 shows, but later on it performance drops. And someone has more, CNN3 has more fluctuations, and CNN2 performance maximum is always less than the 70%. So that means the depth, number of layers doesn't help that much, but number of kernels, a larger number of kernels help us here. Training losses, again, similar thing, similar pattern. We see that we accumulate the losses over the entire training samples. And we see that CNN2 has the lowest loss, but we know that CNN4 has a better accuracy. So that means even though it has slightly lower loss, but it has a better generalization performance. And for precision results, we see the most of the models struggle, but CNN4 achieved the 50% dementia precision at the last epoch. And we know that we have only 1.5% dementia participants in our data set. But all models performs better for healthy cases. And they have done around 90% precision results. For recall results, CNN4 again performs better than the others. Even though it's slightly lower, 34.2.9% average epoch, average results over the epochs. And that is 43% better than the CNN2. CNN2 has the most stable performance, but lowest overall performance. And CNN3 again showing the higher volatility. MCA recall is also average is around 45 to 55%, 50%, but CNN4 performs better. We also compared the CNN with the SBM support vector machine, but support vector machine completely fails to detect the MCI in the dementia cases, 0% accuracy for precision recall, even though it has a good accuracy performance, but that is mostly for healthy patients. But CNN can capture the special patterns that we saw before compared to the SBM. So overall, yes, CNN has some potential um, for dementia screening. And we also use some other technique, which is sampling data augmentation to improve the minority class detection. Large kernels helps us here compared better than the depth and weight, increase in the depth and weight. And CNN significantly outperforms SBM. And we know that we have a severe class imbalance that is hampering our metrics. We can use the generative adversarial network to generate the more minority classes to address severe class imbalance. Thank you.